Hello, and welcome back to the course. So we're going to look at different types of isolated singularities of holomorphic functions, and we're going to look at or prove the Riemann extension theorem for holomorphic functions. So this is subsection 521 in the book. So suppose that we have an open subset and a point in this subset. And a function f, which is defined on u minus this point. So you define everywhere in u except that point. Suppose that that function is holomorphic, then we say it has an isolated singularity at p, right? It's basically just not defined at this isolated point. That's what we mean by an isolated singularity. Now, such a singularity is called removable if there's this holomorphic function. Basically, if we can extend through the singularity, so that means that if there exists a holomorphic, let's call it capital F, defined in all of u, such that little f is equal to capital F wherever those two are defined, right? So that's what a removable singularity is. Now, a singularity is a pole if, on the other hand, we have that the limit as z goes to p, as we can't really define it to be an infinite value, but maybe we can define it to be an infinite value. So that's what we mean by a pole. So it's not quite holomorphic, right? But you have sort of a reasonable definition of what the value should be. It should be infinity. Okay, it's maybe not a complex number, but it's at least in the Riemann sphere, right? So that's what we mean by a pole. It's the limit exists. Well, if we think of infinity as existing, right? So that's what a pole is. Now, if it's neither a pole nor removable, we just say it's an essential singularity. Basically, think of it as essential singularity is a singularity we can't quite get rid of in some way. All right, so a couple of examples. So a pole, a typical example, 1 over z. It's, as z goes to 0, 1 over z goes to infinity. So that is a pole. An essential singularity, sort of a typical example of that, is the exponential of 1 over z. Now, why is that an essential singularity? Well, if we approach from the positive side, right, if from like just real z, but from the positive side, it goes to plus infinity. If we approach from the negative side, we go to 0, right? So that's not, it's definitely not extendable even as a continuous function. So it's not a removable singularity, and it's not a pole either because the limit doesn't exist. All right. Now, let's look at the Riemann extension theorem, right? And basically, the Riemann extension theorem tells you that the only way to have an actual honest singularity is for the function to somehow, in some way blow up. As we approach z, we get, somehow bigger and bigger values. Basically, if you have a function with an isolated singularity, that is bounded, and really it's enough to, because we're just thinking of near p, so it's enough to think near p. So if f is bounded, then this p is a removable singularity, right? So there is no bounded essential singularity, for example, right? So that's what the Riemann extension term is, and it's actually kind of cool in how it's proved. So, and it's kind of a magical theorem if you think about it, because it's just bounded. Bounded is it doesn't seem like it should be enough. All right, so how do we prove it? So let's define a new function g, and let's define it in this way. Let's take f and let's multiply it by z minus p squared. Right. It's basically we're going to sort of squish the values near p into 0, right? And so we're going to define g at p to be 0. So now we have this function g defined on all of u, right? Well, G is holomorphic, where F was holomorphic, right? Because, well, right. We're just multiplying by Z minus B squared, right? Now, at the origin, this is where we use the boundedness of F. If we look at the difference quotient, we notice that the difference quotient, well, G at P is 0, right? So it's just G of Z divided by Z minus P, and I really just divide one of these Z minus P's, right? This is what that expression is, and it's clearly 0, right? Because F is bounded. So, and I have a bounded function times something that goes to 0, so the limit here is 0. All right. Now that means that G is complex differentiable at P. Now it's complex differentiable everywhere else, so it's holomorphic on U. Now furthermore, G is 0 at P, and G prime is 0 at P, right? I mean, we just computed that over here, right? So that means that the G has a 0 of order at least 2, maybe more, but at least 2. All right, so let's call the order K, and so we write G as Z minus P to the K times some H, some holomorphic function H. H again is holomorphic on U, right? And K is bigger than or equal to 2. Well, now we have a formula for F, right? F is simply, because K is bigger than or equal to 2, so K minus 2 is bigger than or equal to 0, so this is a wonderful holomorphic function, and that's exactly what F is. So P is removable singularity. Now, this is really an amazing theorem, right? I mean, you definitely don't expect anything like this for anything but a holomorphic function. I mean, it's a very surprising theorem, right? And the proof is kind of insane, right? But it follows from this, from this point that we proved this amazing fact that if you have one complex derivative everywhere, you suddenly have infinitely many complex derivatives, and you have a Taylor series and all, power series and all that, right? And so we just needed to make sure that we find a function which has a single derivative at this single point, right? And suddenly it has all these other derivatives and it's holomorphic, right? So let's look at some exercises, right? So if we have a function from the puncture disk to the puncture disk, and let's suppose it's an automorphism, meaning it's a biholomorphic map, right? Then you can prove that it's actually just a rotation, right? And you use Riemann extension theorem, right? Basically, you want to, use what you know about automorphisms of the disk, and you want to use the Riemann extension theorem to get an automorphism of the disk. All right. Now, the Riemann extension theorem is, as we just mentioned, I mean, it's an amazing theorem only for holomorphic functions. It's not true for functions that are not holomorphic, sort of the standard example of something that's bounded in the plane in R2 minus the origin, but it's not, it doesn't extend in any way, right? It's this example from calculus, right? Calculus of two variables, right? X, y divided by x squared plus y squared. That's actually a function whose values are between -1/2 and 1/2, but it's depending on how you how you approach 0. So if you approach, for example, along different lines, you will get different numbers. So this is a function. It's real differentiable, and it's infinitely real differentiable. It's really nice, actually. I mean, it's a rational function. So it's a very nice real differentiable function. So not a holomorphic function, real differentiable function. It's bounded, it has an isolated singularity, but it does not extend through in any way, not even continuously. All right. Now, poles are precisely, well, it's let's say, poles are where the function blows up but it actually blows up exactly to a finite order. This is related to the fact that we had zeros, all zeros of holomorphic functions were always zeros of finite order. There were no infinite order zeros. So similarly, if we blow up, if we go to infinity, no matter how the limit is infinity, then it has to be to a finite order, right? So let's prove this. So suppose that we have an open set, some point P in the set, and holomorphic function with an isolated singularity at P. Now, if P is a pole, then there exists some K such that if we multiply F by the kth power of Z minus P, basically we're saying we can sort of cancel out Z minus P to the K. 1 over Z minus P to the K, I mean. So that has a removable singularity at P. So this G has a removable singularity at P. Meaning, right, what does it mean if I divide by Z minus P to the K? That means that F is G of Z divided by Z minus P to the K, where G can be made holomorphic at P. Now, conversely, if there exists a K, some integer K, such that this guy is the same expression, is bounded and therefore has a removable singularity by the Riemann extension term, then F has a pole or removable singularity. I mean, if F has a removable singularity, then for every K, if I multiply by Z minus P to the K, it still has a removable singularity, right? So it could be a removable singularity or it could be a pole, but it cannot be an essential singularity. All right, so let's prove this. Suppose that F has a pole at P. So we're looking at part 1. So then F is not zero in some punctured neighborhood, right? I mean, it goes to infinity, so it can't be, zero arbitrarily close. So there is some R. So if I look at the punctured R disk around P, then F is not zero there, right? So 1 over F is bounded, right? It really goes to zero, right? But it's bounded in some, in this in this guy, right? So that means that by the Riemann extension, there exists a holomorphic H such that H is equal to 1 over F, right? All right. So we can extend 1 over F through P, right? Right. So H is holomorphic in the entire disk. All right. So now, since 1 over F goes to 0 as Z goes to P, that means that H has a 0 at P. So, so it has a 0 of some order K, right? So we'll write H as Z minus P to the K times some phi where phi is not 0 at 0, right? So we factor out as many Z minus P's as we can, right? We know that we can do this. All right, now this is just to keep track of what is what, right? So we're on a new page. So now since H is not, it's 1 over F, so it's not equal to 0 in this punctured disk, then this C, we know it's already not equal to 0 at P, but it's actually not equal to 0 on the entire disk, right? So therefore, 1 over C is holomorphic in the disk, right? In the entire disk, including at P, right? So for Z in the puncture disk, G is equal to Z minus P to the K times f. That's just by definition. And then f is, well, what is f? 1 over f is h. H is z minus p to the k times c, right? So, here we can divide by this, right? Because we're not, so we're in the punctured neighborhood. But notice that, well, we can cancel these guys, right? We get 1 over psi, and 1 over psi, well, it's holomorphic, right? So therefore, this g has a removable singularity at p, right? And, so this 1 over psi is exactly the guy that we want. All right. So the converse, for a converse statement, let's suppose that g has a removable singularity. All right, so g is z minus p to the L times some phi, which is not zero. And f, well, f is, it's really g divided by z minus p to the k, right? And so we'll just plug in what the g was, right? Now, f will either go to infinity, and that's if k is bigger than L, because then we're going to have z minus p in the denominator, right? And in that case, f has a pole. If k is less than or equal to L, then this is a nice bounded function, this is a nice bounded function. So then f is bounded, therefore has a removable singularity at p. All right. Now, this k, if we take the smallest k, and this is just like for zeros, we're going to call this smallest k that we need the order of the pole. And again, the point is this is always a finite number for holomorphic functions, right? So for a holomorphic function with a pole, the smallest k, such as z minus p to the k, has a removable singularity, so it's bounded near p. That's called the order of the pole, right? And a pole of order 1 will be called simple pole, just like we called a zero of order 1 a simple zero. All right. Now, if f has a pole at p, then you can really think of it as being a function like this. It's a holomorphic function, a non-zero holomorphic function, g divided by z minus p to the k, right? That's really the way that you want to think of poles. So it's sort of like factoring out, zeros, so factoring out poles, right? We're just putting it into the denominator, right? Now there's this symmetry between zeros and poles, as should be expected, since we keep talking about it. It's 1 over, right? So if f has a zero of order k at p, then 1 over f has a pole of order k at p. Now if f has a pole of order k at p, then 1 over f has a removable singularity. So we could really think of 1 over f as being holomorphic, and that holomorphic function has a zero of order k at p. So it's a little bit harder to say than the first one, but basically, if I have a pole of order k, then 1 over the function has a zero of order k, and vice versa. If I have a zero of order k, 1 over that function has a pole of order k, right? With this technicality that we're really talking about, the extension of the function. All right. So more precisely, if it's a pole or removable singularity, we can always factor out a z minus p to the L, where L is some integer, right? So if L is positive, it's 0. If L is negative, it's a pole. If L is 0, then, this was just not a 0, right? neither a zero nor a pole. Now, so the zero is of order L if L is positive, and it's a pole of order minus L if L is negative. Right, so there's this sort of symmetry, and like we said before, you could think of a zero of of order zero being a function that is not zero. But you could also think of it as a zero of order minus 2. Well, that's really a pole of order 2, and vice versa. Although it's not really useful to say that, but sometimes it's sort of you can see this symmetry in some of the statements. All right. Now, here's a useful exercise that parallels the result that we had for zeros, which said that if I have a zero of some order, let's say of order k, then the function really locally behaves like z to the k. Well, same thing for a pole. It locally behaves like 1 over z to the k. And this is the exercise. So suppose that f has a pole of order k, then there exists a holomorphic g, which has a non-zero derivative. So it's 0 at 0, but it has a non-zero derivative such that near p we have that the kth power, 1 over the kth power, is f. So we are basically taking a root, right? All right, so that's it for today. So next time we're going to look at how the Laurent series relates to singularities. All right, so see you then.